else if you didn't raise your hand. If you don't have a link to the homepage, send me an email and I'll send it to you. So where were we? We're talking about the objectives of science. The objective of science is to produce theories that help explain and predict the natural world. What's the natural world? It's the world we cannot control. The laws and principles that govern our interactions with the world that we cannot change. Those are the natural world. So the first step in coming up with a theory, or I would say the foundation, it's not necessarily first. The foundation of a theory is the vocabulary of the theory. Theories have three parts: vocabulary, axioms, and interpretation. The vocabulary is the basis of the theory. It's most important. As a matter of fact, I would say getting the right... So there's a great theorem called the fundamental theorem of calculus. Isaac Newton is famous for proving it. It's one of the landmarks in the history of science. I proved it as a homework problem. It was given to me one day's assignment, prove this theorem. And I did it. Does that mean that I could have been Isaac Newton? I mean, I proved the theorem, he proved the theorem. What's the difference? The difference is very important. Newton discovered the concepts, the vocabulary in terms of which the theorem was stated, derivatives and integrals. Those were his ideas. The second law of motion, force equals mass times acceleration, that's just what force and mass are. Once you define them correctly, the laws of motion just fall into place. It's coming up with the right concepts as the basis of a theory. Identifying what is importantly alike, what categories we should give names to. There's a reason for that. Scientific laws are generalizations. Things like, not true, but all dogs are blue. Or here's a true one, all healthy dogs have hair. You generalize over categories. In order to come up with useful generalizations, you need the right categories. If you put whales and swallows in the same category, that would be weird. If you put swallows and bats in the same category, if your category is small flying things and big swimming things, you get sharks and whales, swallows and bats. There are much fewer useful generalizations you can make. So identifying the right concepts is the foundation of scientific thought. Here's another interesting example. Planets and stars. Did we get to this slide last time? No. So we have three things: planets, stars, and the sun. All things you can see by looking up at the night sky. Planets and stars look the same. You might have thought Venus was a star. Venus, the biggest light you see early in the evening is actually not a star. That's Venus. There are 5 of them. There are 5 what look like stars in the night sky that are really planets. That's been known for thousands of years, ever since the Sumerians discovered that. How did they know? Does anybody know how they told the difference between planets and stars? Retrograde motion. Hey, you're using big words, man. Somebody said that, but I can't detect it when I look. They all move across the sky at night, but the stars move the same way every night. The planets take different paths throughout the seasons. Planet asterisk, wandering star, that's what the planets were called. So they noticed these things are different from those things. But what they didn't notice was they were standing on one. This thing is like that thing. This doesn't look anything like that. And those other things, the ones that don't move, they're like this thing. Now that's an important discovery. Putting things in the right categories then allows you to make generalizations. So things that are deeply alike or deeply different may appear alike. Mars and Polaris is a star, look the same. Bats and swallows look the same, but they're different, fundamentally different. So they look just alike. They would appear naively to be in the same category. Mars and the Earth look very different. The Earth looks like this, and Mars looks like a star. Bats and whales look very different, but those things have deep similarities. So it's hard to tell just by looking what should be put in the same category and what shouldn't. And it's the foundation of scientific thinking. It's the discovery of the correct categorizations of things. For example, here's an example of classical mechanics. It's a branch of physics. Three things. Vocabulary of classical mechanics is objects, mass, force, distance, time. Axioms are the laws you learn in Physics 1. Conservation of energy, conservation of momentum, Newton's laws of motion, law of universal gravitation. You might have learned the drag equation or some simple form of the drag equation. Those are all things that are true, but notice we can't even make those statements without first identifying the vocabulary in terms of which they're stated. You can't just start. This thing's still on? Now, interpretation. All that stuff is no good without knowing how to apply it in the actual world of experience. You do that by, for example, first you have to know when you can use the theory. When can you use classical mechanics? Things can't be too big, they can't be too small, they can't be moving too fast, they can't be undergoing a chemical reaction, and they can't be bending and breaking. But if things are just bumping into each other, and they're not deforming, and they're not undergoing chemical reactions, and they're not too big, and they're not too small, and they're not moving too fast, then you can apply this theory very profitably. Now, how do you map these vocabulary items? How do you get from the world of experience, the world out here, to the symbols in your notebook? You have to know how to interact with the world of experience to get the model. And so force is what you measure on a spring scale, mass on a balance scale, time on a stopwatch, distance on a ruler, etc., etc., etc. Those are all part of the theory. They're not separate from the theory. Without those things, if Newton just said F equals ma and didn't tell us how to measure F, m, and a, it wouldn't mean anything. It's got to connect to the real world via some interpretation, a methodology of the use of a theory, of its application to the world of experience. So, here's the big picture. We gradually conquer chaos, hopefully getting ever fewer punches in the mouth by describing reality with ever greater precision, but never perfect precision. Never perfect precision. Now, there are 5 laws of gravity historically. There's Aristotle's, Galileo's, Newton's, quantum gravity, and Einstein's theory of gravity. None of the two agree with each other. They all make different predictions. They're all inconsistent with each other. Which one's the best? Depends on what your purposes are. Most of them are still in the physics book. Most of them are in your physics book. 4 of them are. One of them is not. Which one's the worst? Aristotle. Now, if it's not true and the others aren't exactly true either, why is it left out? What's so bad about it? Well, the thing is, there is no situation where Aristotle's law of gravity is more profitable to apply than Newton's with the drag equation. So it becomes outdated because there's a theory that's better. There is no purpose for which you would apply that you can't have a better tool. So that one gets left out. But the others, they overlap. They have overlapping areas of application, and they're still all useful to have in your toolbox. They're still all useful to have in your toolbox. All right, that's the end of that set of slides. And the next one is here. The scientific method. But I don't call it that. I call it the methods of science. The phrase the scientific method puts too much importance on certain details that we're going to discuss aren't that important. So here's a dictionary definition from the Oxford English Dictionary. The scientific method is a method or procedure that has characterized natural science since the 17th century, consisting in systematic observation, measurement, and experiment, and the formulation, testing, and modification of hypotheses. Sounds like something out of your chemistry book in high school, like it's in my biology book, or something like that. First page. What is science? Here's the method. But let me ask you something about the supposed scientific method. Suppose you did science some other way. You kept the goal the same. You're looking for theories to explain and predict the natural world. But suppose, instead of doing that, you did something else. Like you used a deck of tarot cards or a Ouija board. Or you rolled dice and made up a theory by rolling dice. Would those be just as good? Would that be like, they play football one way in Australia and they play football one way in the United States. There's American football and Australian football. They're just different games. You do them different ways. They're both good. So the question is there something really cool about this method, or is it just one way of approaching it among many? What, if anything, are the virtues of that method? And that's an open question for people to raise their hand and say answers if they have any ideas, thoughts on it. It works. Yeah? It's repeatable. What else? Man, the undergrads this morning were all over it. They were like, yeah, y'all must have taken a few blows. Or not to speak so much. So there could be several other answers. Okay. Now, it's repeatable and it works. What if it was repeatable but it didn't work? Didn't give you accurate prediction? Would it be cool? No. What if it worked but it wasn't repeatable? No, that's the one I'd go with. I'd go with the one that works. So these are not arbitrary rules like the rules of football. These are what they are because they work. But why didn't they work? Why didn't it work earlier? Why was there a thing called the scientific revolution where people started doing this? How did they learn what worked? We're going to talk about that for a while because it's a very important question. What enabled them to do that? All right. So let's look. I'm going to tell you 3 stories. So we're going to look at the mindset behind science, and we're going to look, and it's difficult to examine because we're so steeped in it. We grew up in it. You grew up with physics labs and chemistry labs. And it's part of our culture now. So telling somebody about the mindset behind science is like trying to tell a fish about water. Say you're having a conversation with a fish. He's a very intelligent fish. He speaks English. And you say, how's the water today? And the fish says, oh, how what? The water. The what? You're in water. What do you mean I'm in water? The fish has never been out of the water. He doesn't know the difference between being in the water and being out of the water. What's water? It's the stuff you're in. I'm not in any stuff. Okay, let me show you something. You scoop the fish out of the water. Now you're not in the water. Now you're in the water. Okay, I get it. I get it. So, fish out of water. Fish out of water. Investigation of the laws of nature out of science. Or just investigation without the principles that led to that. So let's take ourselves out of the water for a minute. I'm going to tell you some stories about what not science looks like. And here's one thing it looks like. We see that bodies which have greater impulse, either of weight or of lightness, if they are alike in other respects, move faster over an equal space and in the ratio which their magnitudes bear to each other. That is written by Aristotle in the book Physics, book 4. Anybody put that in English? I mean, what's he saying? That's right. That's right. In the ratio which their magnitudes bear, twice as heavy falls twice as fast. Is that true? Is it close to true? Could a reasonable person believe that for 10 minutes upon serious investigation? Not really. Not for an hour. Okay? None of you would believe it for an hour if you were really interested in figuring out whether it's true. Maybe you would, but many of you wouldn't. So here's the question. Okay, Aristotle's, this is the only law of gravity that's still not on the book, so to speak. But it was the one that held sway for the longest. This was the law of gravity for 2,000 years. Galileo's has only been around for 400 years. I mean, this was the champ for a long time. But it's obviously, easily demonstrably untrue. It's easily demonstrably untrue. What, were they crazy? Not only did Aristotle believe this was taught in universities for 2,000 years. Professors, people who do what I do, wrote this on the board, but instead of pointing out that it's not true, they said, write that down and remember it's a law of nature. And everybody did. And they grew up and told the next generation. And it happened for 2,000 years. Apparently, not one person on record, not one person is recorded for 2,000 years as having dropped a 5-pound rock and a 10-pound rock and seeing if they hit the ground at the same time. Wow. What? Why? How? What? Seriously? Was everybody stupid? This is nuts for 2,000 years? And it wasn't just one person or one part of the world. Nobody in the whole Western culture ever tried it. Okay, that's what science doesn't look like. Before we ask what were they thinking or not thinking, what were they feeling or not feeling that led to that? I mean, here's what you could ask yourself. What if you'd been born in the Middle Ages and your professor had told you that? What would you do? What would you have done if you hadn't grown up steeped in the culture of post-Enlightenment culture? Probably, I have to say, probably I'd do what everybody did, is write it down and believe it. What's changed? To answer the question, what's changed? But I wouldn't believe it for a second now, and neither would you. Why are we different from the way we would have been back then? To get an idea of what's changed, let me tell you 2 other stories. This is a true story. This is a guy I know. He's not a famous physicist. His name is Cal Burgoyne. He taught mathematics and science in Micronesia doing missionary work. And he had this conversation with a 12-year-old girl. He said, okay, what's 5 times 1? And she's like, I don't know. First, he sort of gets multiplication in order. 3 times 2 is 3 plus 3. You do it 2 times, and so on. So he says, okay. So then he asks her a few things. He says, what's 5 times 1? It's like the times 1. Repeat something 1 time, that's a little confusing. I don't know, sir. And he says, well, 5 times 1 is 5. She says, okay. So he says, all right. What's 5 times 1? 5. Good. Now, what's 3 times 1? And she says, I don't know. And he says, well, it's 3. And she says, okay, got it. He says, what's 5 times 1? It's 5. What's 3 times 1? 3. Okay, good. What's 7 times 1? I don't know, sir. Well, it's 7. And he sees, she gets it. Ah, I thought maybe that was it. He could hear 7. Okay. He says, all right. He sees the light come on. Now he says, okay, all right. What's 9 times 1? I don't know, sir. And he says, come on, you can do it. I know you know. What is it? What's 9 times 1? Come on. And she breaks down crying. Just breaks down sobbing. Anybody have any idea why? Okay, so don't let the cat out of the bag. See if anybody can figure it out. You say because she was what? She thought she was dumb. Most people don't cry when they think they're dumb, but they will hide their face. Here's what's happening. In that culture, as a child and as a female, so especially as a female child, she is not allowed to have an independent thought. She's not allowed to do or think anything she hasn't been told to do or think by an authority figure. This guy is pressuring her to figure it out for herself, to have an idea. to figure it out without being told, to be an independent thinker. It's not allowed. Her parents have spanked her when she's been an independent thinker. She's been drilled into her, don't do that. But she's also been told, do what your teachers tell you. Do what adults tell you. So he's telling her, she doesn't want to disobey, but she doesn't want to have an independent thought. He puts her in an impossible situation, and she breaks down. She doesn't know what to do. It's not like that girl was weird in that culture. That was normal there. Women and children not allowed to believe anything unless they've been told it by an adult man. Crazy. Did nobody stand up and go, hey, wait a minute. What if they figure it out and they're right and you're wrong? Nobody just, shut up, sit down. Okay? Just total insanity, right? Just like the Middle Ages. Here's a third story. Friar Giordano Bruno. Friar Bruno was burned alive in 1600 on the order of Pope Clement VIII for the following crimes. This is what he was accused of. I'm not going to read them all. It's a long list. Holding opinions contrary to the Catholic faith and speaking against it and its ministers. Holding opinions contrary to the Catholic faith about Trinity, divinity of Christ, and incarnation. Holding opinions contrary to the Catholic faith pertaining to Jesus as Christ. Holding opinions contrary to the Catholic faith pertaining regarding the virginity of Mary and the mother of Jesus. It's starting to sound like cider house rules. And so on. So they burn him for this. Not for, just for, nobody said it was wrong. Look at the list. They don't say he's incorrect. They don't say he was spreading falsehoods. They just said, the authorities said this, you said something else, you die. And it's not like and it wasn't just one person in charge thinking that crazy person in charge thinking that's how it should be. It was a room full of people that said, yeah, of course. It's nuts. All right, 3 stories of what appear from our perspective to be insanity, all pre-scientific, but all with the same theme. There's a common thread there, and when you see that, then you can see what's behind the Enlightenment and the scientific revolution. What is the common thread? What do we know that Aristotle, medieval professors, Micronesian traditionalists, and Pope Clement VIII did not? And by the way, I'm not saying that to belittle the church or religion. I go to church. I run a Bible study for Texas Tech students, for both believers and non-believers. You can email me if you're interested. But that was evil. That 1600 Pope Clement VIII doing that was. You have to say compared to what? I mean, was anybody really behaving better back then? I don't know. But by our standards, that was very primitive. What do we know that they didn't? The same thing in all 3 cases. It's the same thing in all 3 cases. Yes. What people believe is true might not actually be true. And it doesn't matter who they are. It doesn't matter if it's Aristotle, the Pope, an adult male, or whatever. Nobody, no institution, no human being, no matter who they are, is invested with power over the truth. The truth is outside of and above any human institution, and everybody can see it for themselves if they look. There's no office you can hold that entitles you to a special privilege about truth. So truth is above and outside of any human institution. That's what they weren't getting. That was the scientific revolution, was believing that. Galileo was the first person on record who said, in the words of Judea Pearl, I don't care about Aristotle and his fancy books. I'm not going to idolize Aristotle anymore. I want to know if what he said is true. And the truth about the rocks is not in the book. The ultimate truth about the rocks, the place that truth lies, is in the rocks. And that's where I'm going to look. I'm going to look at the rocks with my own eyes, and I don't care what anybody says. What about the story from Micronesia? The truth about arithmetic is what it is. It doesn't matter who says what. If somebody figures it out for themselves, they could be right. And the truth of what they figure out should be respected no matter who they are. There's no privileged access to the truth. Third story, Father Bruno. Agreeing with the authorities is not what's important. Being right's what's important. And by the way, even being wrong probably shouldn't get you burned at the stake. So all those stories reflect a mindset that was actually, that will enlighten you will explain a lot of what you can't seem to explain about people's behavior around the world, in some places even today, but everywhere before about 1600. No respect for the truth. They entertain the idea that the truth is managed by certain people, whoever the powers that be are. Yes.
It's also the case of the Catholic Church. We have religions in southern Kentucky.
Of course they did. Of course they did. And but people accepted it. I mean, if everybody had been saying, "Hey, wait a minute, the Pope might not be right," and just people were going around and bashing skulls, it would be one thing. But it was pretty much peaceful interactions. It was like, "Yep, Pope's always right." Everybody just, yes, sir. I had a very interesting story told to me by, if you're a TCS major, you might have had him, Dr. Yujuan. No, it was not Yujuan. Dr. Zhang, Wan Lin Zhang. Anybody had him in a class? So, at the time, our dean was Pam Ibeck. And Dr. Ibeck said, "The computer science department has a retention problem. I want you to look into how you can fix it." And Wan Lin was complaining to me. He said, "Look, the dean said we have a retention problem. I want to see the data." She just said, "You have a retention problem." She didn't say, "Here was your enrollment here." He said, "Now, if it was in Singapore and the dean said you have a retention problem, I would say, 'Yes, ma'am, we have a retention problem.'" And he bowed like that. He said, "But I've gotten used to a different way of thinking now, and I don't just take her word for it." All right. No one has privileged access to the truth. That is the difference between science and voodoo. That's the difference between science and voodoo. Scientists and witch doctors are both experts. They're both people that people go to learn stuff. You go, "Hey, what's the answer to this question that nobody else can answer?" But here's the difference. A witch doctor says, "Listen to me. I have special powers to talk with the spirits. Take my word for it. I am like the Pope, like an adult male, like Aristotle. I'm to be idolized. I have power over the truth. It's not outside of me somewhere. It's inside of me." A scientist says exactly the opposite. Don't take my word for it. Don't take my word for it. In fact, that is, if anything, the motto of science. The Royal Society of London, the oldest fraternity of scientists in the world, has as its motto, "Nullius in verba," nothing on the word. To paraphrase, don't take anyone's word for anything. If anybody's ever trying to sell you something and they say, "Trust me," when somebody says that to me, I say, "My grandfather told me how to identify who you can trust." They don't say, "Trust me." They show you that they're telling the truth. They're transparent. You can say your professor's grandfather, or you can just say, "My grandfather told me." Stretch the truth a little bit. So, if you're not supposed to believe anything anybody says, how do we get work done? How do we discover? What's the point of communication? What's the point of communication if I don't believe? I'm not supposed to believe you. The point of communication is this. What I'm supposed to do for you I'm not supposed to try to control your thinking, make you believe something. What I'm supposed to do is turn on a light and shine it somewhere and say, look there, at what I found. Do you see it too? And if you see it, you don't have to take my word for it. And that principle, that I don't control the truth, all I do is shine a light for you to see. That's how we communicate with people we respect. That's effective communication and effective persuasion, is not trying to control the other person. And that determines a lot of the methodology in different branches of science. Now in mathematics, for example, if you have a new theorem, you say, here's a theorem. I know this is true now. I figured it out somehow. I'm going to publish it. I write a paper with a statement of my theorem. You can't publish a paper with a statement of a theorem. That's not a paper. They'll reject it, mail it back to you. Email it back to you. What's missing? A proof. What's so important about a proof? Don't take my word for it. Read this and see if you believe it. You can see the proofs. Most people skip the proofs in their calculus books. Understandably, they haven't been given the wherewithal to read them. But those are important. It's important to go through at least a few. It's important that they're at least there. And here's the reason. It's reasonable to believe what your teachers tell you is probably true. It's reasonable to believe that because your calculus book says that the fundamental theorem of calculus is true, it's probably true, and you can count on it, and it's not irrational of you not to investigate it. You don't have time to do the proofs and experiments of everything you're being taught. It's being jammed down your throat like a fire hose too fast. But when you do that, when you believe what I tell you, you're acting as a student of science, not as a scientist. If you want to put your scientist hat on, then you don't believe me. If we're talking peer to peer, you shouldn't believe anything I say. All you should believe is what I shed light on. So those proofs are in the book, just because in principle, if you wanted to, you can check them, and then you know, not because I told you. There could be nobody else in the world. You don't have to believe anything anybody says. You know the same way Isaac Newton knew. Similarly, if I have an experiment, suppose I did the following experiment. Suppose I do some experiments, and I find out that 90% of college students will murder someone if I put on a lab coat and strongly urge them to do it. I don't have to threaten them, point a gun at them, even offer them a bribe. I just talk very sternly to them. Suppose I found that out. That's true, by the way. We'll talk about that on Wednesday. Suppose I found that out. Could I just put that in a paper and publish it in a psychology journal? It's a very interesting fact. It was published in the 60s or 70s. No, I can't just say that. 90% of people will do this. That's not publishable. They'll send it back to me. What's missing? The experimental data, but not just the data. I can make up the data. You believe me that I got this data right. Description of the experiment so you can do the experiment if you want to. I need to describe it in enough detail that you can perform it and be expected to get the same result so that you don't have to take my word for it. Once again, not taking nothing on the word, only shedding light. Now, here's another fact about it. Newton was a genius. Einstein was a genius. No doubt about it. Very few people could have made the discoveries that they did. Turing was a genius. Alonzo Church was a genius. We're gonna investigate their discovery. They're just as deep and just as hard as anything in science. What we're going to be studying this semester is as hard as the theory of relativity. It's as hard as quantum mechanics. And most people won't get it all the way. Might not have time to get it all the way. But you will probably get enough of it that you see that if you wanted to, you could get it all the way. You can understand it, every word of it. There is nothing in science that you can't understand. If you want to learn the theory of relativity and understand it exactly the same way Einstein did, maybe you couldn't have discovered it. Maybe you could. Maybe you couldn't have discovered it But you can understand it and see that it's true, not because anybody told you, but for the same reason that Einstein knew it was true. There is nothing off limits to anyone in science. Now, if you're mentally handicapped, there is. But if you really want to know, and you're not mentally handicapped, there is nothing off limits to you. There is no door that's closed to you if you really want to go there. In that sense, science is equal. We're equal in the eyes of science. In fact, scientific genius doesn't have to do with knowing things other people can't know. It's exactly the opposite. You haven't really made a scientific discovery until you shed light that anybody can see. Scientific genius is making things clear to anybody who wants to look. It's exactly the opposite of any kind of elitism. It's laying out the evidence in such a way that it is objectively clear to anybody who wants to look. So if there's such a thing as the scientific method, then its real essence is reverence for truth. Is knowing that nobody has a monopoly on it, and that is not a trivial fact. It's not something that most people who've ever lived have really had in their hearts. It's unusual. It's rare. Only in certain times and places has the value system that engenders science been alive. And it's alive to varying degrees in varying places. It's not you have it or you don't. You have more or less of it. And scientific innovation and discovery will thrive or not in a culture depending on their values, on the mindset that they have. And I'll show you on Wednesday, more so than on their intelligence. The Greeks were intelligent. Archimedes and Aristotle were as intelligent as anyone who's ever lived. There are even countries today where people have very high IQs, where there are very, very few scientific discoveries made. Because of differences in values, not every society accepts these principles equally. So, there's a guy named Judea Pearl. One of your assignments for Wednesday will be to watch his commencement address at the University of Toronto in 2007. I'll put a link on the webpage to it today. I want you to watch it for Wednesday. And he says to the graduates of the university, he says, you are now entering the army, or I don't know what he says, you are now entering the ranks of the scientific freedom fighters. Scientific freedom fighters. And his lecture is about what science has to do with freedom. And the question he raises, when he calls it a fight, a fight means there's danger. It means, and you can lose. There's danger and uncertainty in a fight. And the question he raises by calling it a fight is his reverence for the truth, are the values of the Enlightenment eminently natural, stable, and self-sustaining? Should we take them for granted? That's the way it normally is and the way it will always be, whether we think about it, do anything about it or not. Or is there a fight going on? Is the shift that happened during the Enlightenment something that could be undone? Is it being undone? And if it might be undone, then it probably is important to figure that out. What exactly is this, and where are the battle lines? Where are the battle lines of the reverence for truth losing ground? Or at least, where is it apt to lose ground? I'll go back to my office now and put the link up, and you can watch the video today. But I want you to think about that. Think about that for Wednesday. Is respect for the truth something that we are always going to have no matter what we do? Or is it something that we need to figure out how to nurture? And if we have to figure it out, what's going on? Where is it losing ground? Where is it gaining ground? Okay, that's all for today. And I will see you on Wednesday. We'll have a quiz on Friday. I hope not, but we might be. I'll have to check. That's what it says now. That's what it says now.
Half the schedules will say NB.
They moved